Transitioning a language model from a conversational chatbot into an autonomous data agent requires it to operate within the strict logic of a database schema. In a text-to-SQL environment, the tolerance for error disappears. While a chatbot can handle an awkward sentence, a database executor rejects any query with a single hallucinated character, leading to immediate operational failure. We use LangChain to provide the foundational componentry for these systems. It manages the prompt templates and standardizes how the model interacts with external data. Traditionally, these pipelines are built as straight, linear sequences, leading directly to the next step, without the ability to look back. The weakness is its lack of recovery. If the model generates a minor syntax error at the end, the entire chain breaks. Executing code reliably requires a structural resilience that a simple, one-way prompt chain cannot provide. To see this in action, imagine a user asking for specific global development indicators. The language model attempts the translation, but it hallucinates a column name, confusing the database schema. Because the system is linear, it has no way to verify the query before execution. It passes the flawed SQL directly to the database. The database rejects the request, triggering a terminal operational error. In a stateless system, this error is the end of the line. The model cannot remember its mistake, so the error message is passed directly to the user. This contrasts with how a human developer works. We read the error log, identify the specific syntax failure, and continuously iterate on the code until it runs successfully. For an agent to handle its own errors, it needs an architecture that allows it to iterate on its failures, just like an engineer. LangGraph provides the architectural solution, moving away from linear chains in favor of a state machine. This replaces the one-way pipeline with a multi-actor cycle, where the model can return to previous steps based on the outcome of its actions. Central to this cycle is the shared state object, a persistent memory hub tracking variables like the original question, generated SQL, and error messages. Every node in the graph receives this object, updates its assigned keys, and passes it forward. This state allows for conditional routing. The graph can check the contents of the state object and decide whether to proceed to the next step or loop back to fix a problem. Maintaining a central state transforms the agent from a text generator into a system that can evaluate its own logic at every step. The first challenge in data querying is the imprecision of natural language. If a user asks, "How is the economy?" a database cannot execute the request. Attempting to generate SQL for such a broad query guarantees a hallucination. We solve this by implementing an ambiguity checker node as the first gate in the system. If parameters like country or year are missing, the graph routes the process to a clarification node, which asks the user for specific details. Once the user provides those details, the state object is updated with the new context. The system then routes the flow back to the start, now equipped with the specific data points required for successful execution. By identifying ambiguity before the SQL is ever generated, the architecture prevents the model from guessing and failing. Once the model has enough detail, it generates SQL and passes it to the executor node. If that query contains an error, like a misspelled table name, the database will reject it. In this system, LangGraph catches that rejection and immediately updates the state object with the error log. Instead of ending the session, the graph routes the broken query and error message to a self-correction node, looping back to the executor with a fix. The model now sees its own failed code alongside the exact traceback from the database. It uses this feedback to correct the syntax or hallucinated column and attempts the execution again. This cycle continues automatically until the query succeeds or the system reaches its predefined retry limit. By automating the try-catch cycle, the agent resolves its own syntax errors in the background, turning a terminal execution failure into an iterative step toward a result. When the SQL execution succeeds, the database returns the data as a raw array of numbers and text. For an end user, these raw arrays are difficult to interpret. The system needs to convert them back into something human-readable. The interpreter node takes these raw values and uses the language model to write a concise narrative summary of the findings. Simultaneously, a chart generator node analyzes the data structure and produces a JSON specification to render the results visually. These two components are then merged by the response composer into a final analytical message for the user. This final stage ensures the user receives a clear answer, while the technical complexity of the database remains hidden. This stateful architecture also enables seamless follow-up questions like, "What about Germany?" or "Show me the top 5." On their own, these short phrases contain no geographic or metric data for the database to use. However, because the system maintains a persistent state, the memory node can pull the indicator and the time period from the previous turn and inject them into the new query. The agent uses this saved context to generate a new query instantly, without requiring the user to restate their original parameters. By combining LangChain's processing power with LangGraph's cyclical logic, we move beyond simple text generation and build resilient, autonomous systems that can manage their own complexity.